The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So we're the real-time ray tracing group, and as we like to call ourselves, Blue Steel. So one thing you might be asking yourselves and wondering from us is, where did we get the name Blue Steel? What does it have to do with this thing we call ray tracing? And this morning when I was sitting up and finishing up the project, I was asking myself the same thing. We're doing ray tracing. Where did we come up with this name? So I'm going to give you a little background on what Blue Steel is. The name came from the first day we got access to our PS3. We went to the student center like a bunch of excited kids on Christmas. And what did we do? We created a mailing list for our group. Didn't even mess with the PS3, just created the mailing list and sat there for about an hour and a half thinking of a name. And somehow we decided on Zoolander's famous face, Blue Steel. And it didn't have particular significance to us before, but as you'll see, it has a lot of historical value. Blue steel is also an alloy, a ferrous alloy. As you can see, we have blue tempered spring steel that many companies, industries use. And blue steel is also a warhead made in the Cold War. But these have nothing to do with our project. To us, and for the purpose of this project, Blue Steel is a distributed real-time ray tracer. And Natalia is going to give you a little background on what ray tracing really is.
Thank you. So, ray tracing, there are two types of two terms that you would generally hear, ray tracing and ray casting. Basically, the idea is the camera is like the eye, and from the camera, rays are cast for each pixel in a picture. And these rays, they intersect with all the virtual objects in the scene. When an object is hit, the color of it is computed. The closest object that is intersected is the object that shows up on the screen. Now,
We should credit these slides. They're Fredo
yes.
from 6.837.
And ray tracing is recursive. It accounts for shadows, positions of other objects in the scene. There's reflection and refraction. For example, if this ray were to hit that object and it is reflected, then another ray is cast from that object in the reflecting direction. And this can go on for an indefinite number of reflections. These are normally specified in the program. Here's an example of the recursion. So the three planes are reflective. They're like mirrors, and there are three spheres in between them. With no recursion, you can see there is no reflection at all. With one recursion, you can see the rays are reflecting just off the side mirrors. At the end, with two recursions, there's also a reflection at the bottom. So it is a reflection of one of the reflections. And this is very computationally intensive because for every pixel, you're casting a ray, and for every object in the scene, you're intersecting that ray with the object and seeing if it's hit. And then if it is hit and it is reflective or refractive, so transparent, then another ray is cast. This scene here is at resolution 1024 by 1024, and recursion depth is 100, and the rendering time in our program was 2.6 seconds. The rendering time for 20 depth recursion was 600 milliseconds, and for 10 was 300 milliseconds.
Many of us have taken 6.837, and in that class we all built ray tracers. A typical scene like the one that is on the PowerPoint right now could take up to a minute or more. Often if you were to do 100 bounces, I think mine would probably have taken over 10 minutes.
We did try different SPUs. This picture we didn't try with different SPUs, but we have tried other scenes with various numbers, and we did get exact linear speed up. So if there were twice as many SPUs, it would be twice as fast. And
okay,
yeah.
So I'm going to talk to you about optimizations that we did. Natalia's told you about ray tracing, and that's only half of our project. The part that we have to focus on is optimizing and meeting that goal of being real time. And for us, real time, you have to ask, what is real time? If we go off of the American Video Standard (NTSC), they define it to be around 27-30 frames a second. So that was pretty much the goal that we set when we set out to do this. And so we took the code and we think, okay, we can split this. This task is easily parallelizable, but we're going to have to do a lot more than that if we want to get it better. If we want to get better rates. So we took advantage of the hardware that we were on, and one thing that on the ray tracing end we had to go crazy with was SIMD. They were pretty much the entire ray tracer never deals with a scalar value. We use SIMD for everything, and in the core of it, we do branch avoidance. So we really try not to take branches because branch misses are very costly on the cell. So I believe there's something like 3 if statements spread across 4,000 lines of code for the ray tracer. We really took SIMD to heart in this. We said, so using SIMD, you can process arrays of structures. So we would trace ray packets of 4 rays at a time, and from those ray packets we would generate hit packets, and then similarly, as you go down the line, we would produce an RGB packet, which is a color, 4 color values tied into one. So at every step we would use SIMD to our advantage. Now Brian's going to talk to you about pipelining.
So of particular importance on the cell is not only what instructions you execute, but the order that you execute them in. Because there is no reorder buffer on the cell, there's no out-of-order execution, and despite the fact that compiler technology is very good, hand optimization and pipelining instructions is still always better. For instance, with our triangle intersection routine, we gained on the order of hundreds of milliseconds of render time. We shaved hundreds of milliseconds of render time off of our render time for some scenes you will see later, just by reordering our calculations in the intersection code. So it's very important, especially on the SPEs. And one other optimization we made was the fact that we coded basically everything on the SPEs. Anything running on the SPEs is coded in C, not in C++. We're not using inheritance when we do use C++ because virtual functions have more overhead with respect to memory, the vtable, and also looking up the function pointers from the vtable. So these are just a couple of the optimizations we made. We'll talk about more later.
Just a quick question. So for the pipeline, you actually reordered instruction statements, not the compiler wasn't very helpful in that respect?
Yeah, so I, on that scene 1024 by 1024 with the spheres, we were getting, Natalia mentioned, with a depth of recursion of 10, we were getting 300 milliseconds. That's with optimized. Without the optimizations, we were getting closer to 500 with a depth of recursion. And this with a depth of recursion of 10. And this we gain that extra 200 milliseconds just by reordering instructions in the intersection with optimization level 03 in XLC. So hand optimization, like Mike Acton said in class, is still very important. And I'm going to hand you off to Mikey now to discuss the regular grid.
All right, so one of the problems, I guess, with ray tracing is that intersections are very expensive. And when you have, scenes with n rays and n primitives, well, you have to generate n times n intersections. So one common acceleration structure is a grid. And the concept is very simple, as the picture depicts. You just take your screen, split it up into a number of evenly sized voxels, place your primitives in them, and then you march your ray through. And you only intersect the ray with primitives that are around the area. And the good thing about a grid is that it's very easy to construct, as opposed to, like, say, a KD tree or an oct tree. Those take on the order of n log n, where n is the number of primitives. Regular grid is order n, where n is the number of primitives. And the reason why we did this is because with an interactive scene, you need to, where things are moving around, you need to rebuild the grid every frame or whenever something moves. So we favored this, this choice of acceleration structure because it was quick to build and easy to traverse. Okay? And now, who's Fish is going to tell you about the fun part of the project.
All right. I was in charge of building the actual physics engine. Our original plan was to do the 6.170 well-known gizmo ball in 3D and ray traced. And I guess if I want to, do you want to show that? Okay, I have it running on this laptop. We didn't quite get it ray traced, but I was going to show you a little bit of what I did as a physics engine. Maybe not. Okay, anyway.
We'll get the demo working and then people can use it later.
Anyway, it was basically a 2.5D version of the example that was just up on the screen. Flippers work, absorbers work, and due to complications, we never did get it fully ray traced. And I guess we'll go ahead and give you the real ray trace demos, which we do have a couple of those.
So their actual demo will be on a little LCD screen here. Hopefully everybody can see how great this screen is. Fortunately, the PS3 needs a specific kind of digital connection to display things in the right resolution when you're writing through frame buffer. So we can't project it onto the screen. Can I do it from here?
Whoa.
Now you got to tell, there you go. Oh no, wrong way.
Ready?
Wait, he's still adjusting it.
Uh-oh.
Oh no.
Okay, we prepared a few demos for you, and these are really just going to show off the ray tracing part of it, and the sort of rates that we got in terms of after we applied our speed ups. Here is a thank you. Here we see both the camera is moving, and we have we implemented full scene functional textures. So you see the checkerboard. It's generated every frame. We use no texture maps. This is completely generated functionally. Bump mapping, as you can see in the large orange sphere, is also done on the fly, as well as blending between two textures using Perlin noise is done on the fly also. Showcased in the center sphere right here, you can see both reflection and refraction. The sphere is transparent. It acts as a glass sphere. So you can see the reflection of the orange in it, but also the warping of the checkerboard as it goes through. this is one of the advantages of, well, spheres are part of one of the advantages of ray tracing, because you can use geometrical equations to define your geometry, versus in using rasterization methods, you have to actually define the geometry in some sort of concrete numerical way. I'm going to go to the next demo. This should showcase some of the lights that we implemented.
So how many frames per second is this?
This should be 15 frames a second. And this, let me reiterate, this is with the refraction step requires at least 2 bounces, so 2 steps of recursion. If we were to turn off if we were to turn that off, we would be achieving, I would estimate 27 frames a second, 28. But then it doesn't look as pretty, so what's the point? You can see kind of, this will be showcased later, but you can see the spotlight. It's kind of moving, it's waving back and forth, illuminating parts of the scene. There's also a point light at some distance around here that's illuminating everything. But it's basically the same set of primitives. If you were closer, you could probably notice that the checkerboard is fully reflective. You can view the scene, this far wall, you can view the entire scene in it. I'm going to go to the next demo. This is with the lights off, so you can get a better sense of what the spotlight is actually doing. If you notice on this orange sphere, we implemented 2 different forms of BRDFs. One was generic Phong shading, and then the other was Cook torrents, which is helps using, particularly with metals and other materials like that. It helps have very bright, specular highlight. And you'll notice as the camera's panning back and forth, the sort of speed ups that we get from we took advantage of certain, we used little tricks to glean speed here and there, like when it's so dark or it's very far away, we stop recursing.
We're over, so.
We are, okay.
Yeah, so if there's
let's see.
do the SPs from 1 to 6.
Okay, I can demonstrate the. We actually enabled it so that you can turn it on either 1 through 6 SPEs using command line arguments. So if let's go to the back of the first demo. If I say just use 1 SPE, we can watch it slowly trot along. And if I were SSH'd in, it would be giving me timing information, so I could tell you exactly. It's really unfortunate that it's not, because it's very linear in its speed up. Right now it says 500 milliseconds. But if I turn it on 2, it drops literally in half to 250. You can get a sense of that from that it's moving like tick, 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 tick versus tick, tick, tick. And then 3, it's a similar speed up. And then I'll jump to 5. It's getting closer. And then when we turn on the 6th, it's this should be about 12-15 frames a second.
So you estimate if you had a dozen SPUs, you could reach.
Actually, it's funny you mentioned that. I think it was the Julia ray tracer or the IRT both of them use 2 cell blades, which is a full 8.
It's a full
8 cores times 2. So they use 16 SPUs. The PlayStation 3, due to certain factors, we're only limited to 6.
Mm-hmm. Is the way you're dividing up the work, each SPU taking one, every 6th raster line.
Basically,
that sounds like. Could you improve on the performance by allocating the rays?
There's the issue there is one of granularity of our distribution,
Right.
and also communication time on the bus. We've designed it such that we can fine tune it in any way we want.
But it seems to me that if you had a kind of a localized bundle of rays, on a single SPU, you might be able to do some optimizations, like treat them as fat rays.
Oh, yeah,
Nearby rays are likely to intersect the same triangles.
Which uses the frosting of
Right.
The entire material system works very much like that. It actually saves on computation based on which rays of the in a packet of 4 have collided with the same element.
Mm-hmm.
And if it does, then it takes full advantage of SIMD to quickly chug through those rays that are the same, and then never call that particular shader again because it's already done the work for them.
Another issue, I think, is
Sorry, we should try to wrap up so that we can get through the others. Any more very short questions? All right, did you guys have any last concluding statements?
Maybe you go through the rest like
Well,
really fast.
Yeah, okay.
I mean,
All right, let's sit
the point
down.
was we had two pieces.
Thanks,
and-
speakers.